All right, good afternoon, everybody. So we're going to start today. We're going to continue on red-black trees. We are going to dive into red-black tree deletion. And then what we're going to do is we are going to go over 3 specific libraries in the C++ STL that utilize red-black trees as their underlying data structure. So we're going to see aggregation, but we're also going to see how to implement deletion and how we can maintain this relaxed balance. One quick thing I want to point out, for the setting up lecture 23, it's a little different. Go into your lecture 22 and just follow those directions. You'll clone a second setup file that will bring in all the rest of the files. And when I upload the grade into Sakai, lecture 22 will contain the results from both lecture 22 and lecture 23. Quick note while you all are getting that all set up. So I have a meeting that that I'm required to attend, and so I will not be able to attend this afternoon's lab sections. The TAs will still be there, and I've asked them to post their Zoom links into the Slack, so that way for those of you who wish to demo that way, you're welcome to do so. And that way you can continue to demo, and the same rules apply. You can either demo today in lab, or you have until Wednesday evening during the TA office hour sessions to continue to demo. As part of that meeting, I want to quickly point out something that I brought up to the lab sections on Monday. Kind of feedback I'm hearing from the sophomores that because of some companies are still having a hard time bringing in internships due to COVID, there's cancellations of study abroad. In addition, companies are making up the internships they canceled last year. So the juniors and the rising juniors and rising seniors tend to be getting the bulk of it. So there's a kind of a real crush on this year's sophomores in terms of finding those slots. What I'm going to be doing in this meeting is I'm actually I've requested and received the opportunity to speak to the faculty and ask if they have any undergraduate research or hiring opportunities available. I should know the answer to that no later than 6 p.m. today. And any opportunity that I can scrape from around the university, I will make sure that you are aware of it and post it on the Slack. So I want to make sure that you all know that we're all trying to fight for you and create these opportunities as best as we possibly can. All right, so what we're going to first do, we are going to build the foundation of a red-black tree node. So what we discussed is last lecture is that it has a data element, and just like normal binary search trees, we have a left and a right pointer. And I asked the class, well, how do we know whether something's a parent? And eventually, how do we get to this idea of knowing what an uncle is? And we realized we had to create a third pointer that points back up to the parent. So what we're going to do is we're going to go through the process of designing a struct based on this red-black tree node. And we also need to keep track of the color of the node. So we're going to revisit enumerated types. So by the end of this, you'll have revisited constructors, destructors, rule of 3, pointers, and enumerated types. So what I would like you to do is I'd like you to go to the file in the include folder, RBTNode.h, and go to line 9. So let me show you what you will see when you get there. You will see the bare bones of a RBT node. And we've templated it, and I've chosen it as a struct because this struct is only going to be called inside the red-black tree class. So by doing this and being able to access the members of the struct, instead of having to use get and access method, it'll be a little easier to program. The first thing I want you to do is before the struct, we're going to write up an enumerated type. And the keyword is enum, and we're going to call it color. Now, an enumerated type, we define it using parentheses like that. And what we do is the values that we want the programmer to indicate will be inside the enumerated type, but they're actually going to translate to 0s and 1s. So just to review, what I want here are the colors red and black. So I'm going to make uppercase red and uppercase black. What this is going to be interpreted by the computing device is 0 and 1. The next thing we're going to do is we're going to define all of the things that we need in order to make the red-black tree work. We need the data itself, and then we're going to define all the elements of the structure. We're going to have a color, and then we're going to have a left, a right, and a parent pointer. So the first thing I want to do is we're going to do t data, or t value, excuse me. So that's the value that we're storing. And then the next thing I want you to do is we're going to do uppercase color and then lowercase color. So color is the enumerated type, and lowercase color there is used as the variable name. The last thing we're going to be doing here in terms of the elements is we're going to create an RBT node pointers. RBT node. We need to template it, and it's going to be a pointer, but we can define them all here. We can say, best way to do is we can do star left, star right, and star parent. And so this allows us to say that all three of these in the row are pointers. Does that make sense? All right, do you have a question? Oh, sorry, you're just scratching your head. Okay, as always, I have the Slack open, so you're welcome to ask questions in the Slack. So the first thing I'm going to do here is I'm going to create a default constructor, and then I'm going to create an overloaded constructor, then we're going to create a destructor, and a copy constructor, and assignment operator. So first, let's create the constructor. So the default constructor is going to be empty. So we're going to say RBT node, and we're going to template this like so. And the first value, we're just going to say value. Remember, we go in the same order to maintain the integrity on the data heap. So by putting the parentheses in there, we call values default constructor. So whatever we template it to, if it has a default constructor, this will call it. Then we're going to say color. Now, does anybody remember from last lecture, when we insert a node into a red-black tree, what is the color initially? Yes, several hands went up. So everybody say it together. Red, very good. So we're going to default this as red, and then we're going to set left, right, and parent to null. And then we put the braces here afterwards. So what this has allowed us to do is we have created a default version of the red-black tree. I'm going to do the same thing, except I'm going to do an overloaded version. And so in this case, the overloaded, I would say const t call by reference, and I'm going to call it value in. And then you can press enter at different stages. Typically, if you have it go over the line, pressing enter and tab like that just makes it look clean, but it will compile all the same as the previous line. So what we would do here is we'll do value in, and that is our overloaded constructor. So let me scroll up just a little bit. In fact, I'm going to press enter a couple times so it's visible to those in the room. And I first want to ask, does anybody have any questions on anything I've done in terms of the design of the node struct or how I've set up the default and overloaded constructors? All right, so the next thing we're going to do is we are going to write our assignment, a destructor. So I'm going to say destruct RBT node. And what do you think I want to do here? How do you think we're going to delete elements from the heap? Yes. I'm sorry? Oh, well, technically, yeah, sure. Yeah, let's do that. Keep for consistency. All right, so what else do we need to do? So how did we delete elements from a binary search tree? What was I'll give you a hint. We used a specific type of traversal. Does anybody remember the traversal we used to delete from a binary search tree? Any ideas? Yes, in the back. Post-order traversal. That's exactly right. So there are two different ways to do this. I'm going to keep it consistent with how I'm going to present it on the exam. You can either go left, right, and then middle, or right, left, and then middle. I teach it right, left, and then middle because in my experience, a lot of students will get the pre-order and post-order traversals if I keep with the left-right ordering. So sometimes that's referred to as a reverse post-order traversal. But in this case, just to make it simple to understand, we're going to do right, left, and then middle. So first, we have a rule. We say if right is not null, then we're going to delete right. So that's going to recursively call the deletion of the right. And then I'm going to say if left is not null, then we're going to delete the left. And that allows us to be able to keep track of everything that we need to do. So that'll clear everything off. And then when we call delete root within the red-black tree itself, it'll call the right and left of all the subtrees, which will clear all of the data off of the data heap. The next thing we're going to do is we're going to write our copy constructor. So the copy constructor is going to take in, we're going to do RBTNode, we're going to template. And now what we're going to bring in is we're going to bring in a const RBTNode called by reference, and I'm going to call this value in. Yes, I'm going to call this value in. And now what I can say is, a copy. So now, because this is a copy constructor, we're going to put value. And because it's constant called by reference and it's the same type, we can access the members. So I'm going to say value, and I'm going to say copy.value. And then everything else is going to be null. So we're going to have color, and I'm going to copy the same thing, copy.color. And then I'll press enter and tab. And then this left, right, and parent is going to be the same. So what we're doing here is we're making a copy of a red-black tree node. So now we're meeting our requirement for the copy constructor. Does anybody have any questions about this? I'll give everybody a moment to continue to type. What we're going to be doing next is we're going to write our assignment operator. And this will be useful when we have to say this pointer is equal to this pointer. This will allow us to be able to actually perform the operations. So we're going to write two of these. The first one, in fact, I'm going to press enter several times, so that way everybody in here can see what's going on. So the first one we're going to do is we're going to write our copy constructor for just the RBT node itself. So we're going to do RBT node. I'm sorry, the assignment operator. Yeah, so RBT node itself. We got the ampersand here. And then I'm going to say operator equals. And when we do that, we're going to say const RBT node, just like this, except instead of copy, I always call RHS for right-hand side, so we know that's an equal sign. So what's the first thing, whenever I write an assignment operator, what's the little trick that I do to try to reduce complexity so we're not doing redundant, unnecessary work? Yes. Absolutely right. We check to see if this is equal to the address of RHS. So if this does not equal to address of RHS, then what we're going to do is we're now going to say that the value is equal to assigned value. So And then we'll say color is equal to, I'm sorry, not assign, this is RHS. RHS.value and RHS.color. And then here we'll return a pointer to this. And then we're going to do the same thing, except now we're going to do stuff with a pointer. So now we're going to have RBTNode templated star operator equals const RBTNode template star RHS. So here, for simplicity, I want to say that if this does not equal the address of RHS, so now we're passing the same thing to itself, right? Bless you. Now I can say this value equals RHS. And we have to dereference this because this is now a pointer, right? Value. And then we say this color equals RHS color. And then we return the pointer just like before. Okay, so let me quickly do that. Let me check to make sure everything I did was right. Okay, good. So let me clear that, make clean and clear. Okay, so I'll put that back up so that way you can type for an extra moment. Does anybody have any questions about anything that we've done so far? Okay, I'll check the Slack as well. So we do have a question in the Slack. We say, why do we need a pointer to this if it's already an address? Because we're returning the actual value itself. So the pointer to this is the location of the specific value that it's pointing to. So the pointer to this is actually the pointer to the object that's holding that value. So please let me know if that addressed your question. I see that there's another question being typed. While that's being typed, let me show you what should happen. When you run make test RBTNode 1, it should, and I'm going to show you the actual tree here in a moment. So what I'm doing is I'm putting in these specific values and I'm using this. So let me open in SRC, test RBTNode 1. And what you're going to see here is what I've done. Let me scroll down here. Is I've created one pointer. I've created a root, and I've also created another pointer to equal null. So that's why, to follow up on the question that was just proposed in the Slack, this helps us be able to return that pointer because it can potentially point to null. So here what I've done is I'm setting the node, and then what I'm doing, notice how I'm passing root left. So I got the root, and I have an initial value that's 15, and I pass root left. And what I do is I pass new RBTNode int and a new value of 4. So right now we do not have any more elements here. So we have 4 over there. I'm just inserting it. I've not performed any of the balancing yet. What I'm doing here in this particular node is I've passed the node, so that was initially the root left, and I'm passing the parent left and right. And what I'm setting up for is the ability to indicate that something should point to the parent, something should be pointing to a child, to the left and to the right. And so for the question about the destructor, it's also going to be available on the video as well as. Okay, so yes, please limit the questions to the Slack. I will have those available. That's also available in the slides. So here we're setting the node's parent equal to the parent. We're setting the color equal to the color, left and right. And so what happened is I am running this, and then I'm printing the values, right? So the value, I'm printing out the value, Remember that in an enumerated type, it just corresponds to a 0 or a 1. So what I'm doing is that if it's equal to that, I'm actually printing out this, what I have typed here. All right, so the question is, can you repeat what is the need for 2 assignment operators? Because we have a potential red-black node, but we also need to write an assignment operator for a red-black node pointer. So it's actually different. If we don't write the second one, it won't actually compile. So please let me know if that addressed your question. Right. So then what I've done is I have functions that I'm eventually going to turn into red-black tree methods. This one I'm doing an in-order traversal, so I'm printing in order, print the value itself, and then I go to the right. And then I do the same thing for pre-order. I print the value, then left, and then right. And in post-order, I print right, left, and then the value. And then I print the level order, and I've included a queue to be able to do this. So what you're going to see when I run everything is that I've set up a tree, and I have an in-order, pre-order, post-order, and level order traversal. So you can use this to verify when you're doing your studies on how to implement this in code. And so at this point, you should now have problems 1, 2, and 3.txt now that you've completed those. So let me put the destructor up really quick to address the Marcelo's question. What we're going to do while I have this up here is we are now going to go into how to actually, so here is everything again, so here's available for you. Here's all the code I just showed you. And what I have presented here, if we see this level order traversal, I have 15 in black, 10 red, 25 red, 4 black, 12 black, 3 red, and then 5 in red. And so now what we're going to do, and so I will leave this up here while I'm describing our next task. What we're going to do is we are now going to find out how it is that we can determine the sibling and the uncle. When we're able to determine the sibling and the uncle, this will allow us to be able to then perform the rotations to meet all of these rules. So in order to do this, we really need to go through the process of understanding pointers and how they go through the tree. You're welcome, Marcelo. So to do this, what I'd like you to do is I want you to go to that same folder and go to RBTNode.h and go to line 75, please. And we're going to write 2 methods. So when you go there, what you're going to see at line 75 is here. So actually, this follows up on another follow-up on a question from the Slack earlier. When I have this equals parent right, by creating a assignment operator with a pointer, we're able to compare the locations, whereas before we are checking values with the other assignment operator. So we have to make 2 in order to be able to perform specific object-oriented programming with a templated data structure. So what we're going to do at problem 4, and I'm going to press enter here, is we're going to write these 2 methods. We're going to obtain a pointer to the sibling and then a pointer to the uncle. So the first one, we're going to say RBTNode. And this one's going to be sibling. And I want this to be able to be called by a const version of the red-black tree. So now we're more familiar with functions and passing elements and call by reference. The benefit of constness is that if we want to do a method that we pass a const version of the red-black tree, we can print it out, we can evaluate the red-black tree without making any changes. So even though it's not necessarily be intuitive to have a constant red-black tree, there are times when you want to pass a red-black tree with the call by reference as const. So we're going to make this const and it will work for us. So first we're going to do our same rule. So we're going to say if the parent is null, then we're going to return null. So this allows us to say, all right, if I'm at the root and I don't have a parent, I can't possibly have a sibling. So now we've protected ourselves. And now what I want to do is say, well, I have methods for if it's on the left or if it's on the right. So what I'm going to do here is I'm going to say, I'm going to return, and I'm going to walk you through this logic. The first thing I'm going to do is I'm going to check to see if parent is not null, that means I'm either a left child or a right child, correct? So what I need to do is I'm going to say, well, am I on the left? So I'm going to say first is on left. And if it's true, that means that the sibling is the right. Otherwise, if it's false, that means the sibling is the left. So now we're going to do the colon, and now we're going to do the tertiary operator. And I'm going to say, if it's on the left, then return a pointer to, turn a pointer to the right. And this should be a question mark. Otherwise, if it wasn't on the left, it means that's a right child. And therefore, I want to return a pointer to the left. So I'm going to say parent left. And so what this particular method does, first I check to see if I have a parent. If I do have one, that means I'm either on the left or the right. So if I'm on the left, my sibling's on the right. If I'm on the right, my sibling is on the left. And so that's what this particular function does, method, excuse me. So now what we're going to do is we're going to write one that gives us the uncle. So it's going to return the same thing. We're going to print our pointer. I'm going to call it uncle. And that will also be const. So in order to have an uncle, what do I need to have? Think about this. Let's remove red-black trees. Yes. Very good. We need to have a parent and a grandparent. So what we're going to do is we're going to check to see if the parent is null or if the parent's parent is null. And the way we're going to do that is we're going to say if, and before, just like before, if we have if parent is equal to null, or parent equals to null, then we're going to return null. So if I don't have a parent, then I definitely can't have an uncle. But if I do have a parent, but we don't have a grandparent, I can't have an uncle either. So far, so good. So the next thing is, now I'm going to determine, we're going to do the same process, except instead of checking myself, I'm going to check the parent. So now it's going to happen, I'm going to say, well, if the parent is on the left, so I'm sorry, I want to return. And now I'm going to say parent is on left. Make sure you put the parentheses. And now what are my choices going to be? So what do you think I'm going to put here? So if the parent is the left child of the grandparent, what is the pointer? Give me the notation for the pointer for the uncle. Yes. Parent arrow. And so I heard that part. So that part is correct. So we have parent arrow, and then what's the next thing? Parent, very good, absolutely right. And then now we're at the grandparent. So what's the last thing I should put? Right, outstanding, 100% correct. So that means that if the parent's on the left here, so this is parent, this is grandparent, and this is where I'm currently at. So if the parent's on the left, that means the uncle must be right. And so we did parent, parent, right. So that was parent, parent, right. So that's outstanding. So who wants to tell me what the other thing here should be? What should I put? Somebody else, yes. Yeah, and is that what you were going to say as well? So parent, parent, left, outstanding. So let's type that together. Parent, parent, left, and then semicolon. I'll zoom out just a little so everybody can see. And so that's what we're going to do. That is going to be what we're going to call problem 4. And now we're going to use this for other methods. What this will allow us to do is perform rotations. We need to be able to determine whether or not something is an uncle in order to meet all of these rules that we went over last lecture. So what I want you to do next is I want you to do test RBTNode.h. And what that's going to do, and first let me check to make sure I updated everything correctly. I have not. So from that folder, you'll run make test RBTNode.h. And so if this compiles, and that means if I've done everything right, what's going to happen is I've constructed that same tree, but now I have several tests that will print out and tell me whether or not a particular node has an uncle. So I actually have constructed an entire red-black tree, and I test even the root and well as both of the parents of the children of the root, because they can't possibly have an uncle because they don't have a grandparent. Could we use the sibling function to also solve this problem by returning parent sibling? That's also very good, and that is absolutely right. So that's the question in the Slack. The reason I presented it this specific way is because I want to reinforce pointers and understanding. But yes, you absolutely could use siblings. So please let me know if that addressed your question. All right, let's text to see that. It did work. And what we see here, and what you'll have if you get it to run, is this particular tree. So it has 15, 10, and 25 say null uncle. I can tell you right now, this is 15, 10, and 25. 15 is the root, so it should come back null. 10 and 25 have null uncles as well. So let me go to the slide where I have this result shown. So this is the specific tree, and we see that 10 and 25 both have null uncles because it doesn't have a grandparent. The next thing says 4's uncle is 25 color black. So we see that 4, we have parent, parent, uncle, 25 color black. So we're doing it well. We go through the rest of these, we'll see that, see if I can, let me move this over. All right, good enough. So 12's uncle is also 25. We see that's correct. And so 5 uncle is 12. And we see that 12 black is what has come out. And same thing with 5 is uncle, 3's uncle is 12. Let me minimize this. We see 3's uncle is also 12. So we've used this method correctly to determine all of the potential uncles throughout the tree. Also, we have proven that if it should not have an uncle, it will return as null. So if you got that working as well, if you do ls, you will now see problem 1 through problem 4 completed. Does anybody have any questions about that before I continue? Okay, so there's the expected output. So now what we're going to do is we're putting this all together into a red-black tree class. The copy tree is using the same method that I have for insertion from before. Pre-order, in-order, and post-order, I'm using the exact same functions, except I've converted them into methods. We see that in the destructor that I have here, all I'm doing is delete tree root, and then it just deletes root. And the reason I'm able to do that is just the exact same way that we were able to use a destructor for a singly linked list and a doubly linked list. We are able to recursively delete all the elements, and by using encapsulation in the way that we have, we're not going to get that double free error. So we're able to clear all the elements off of the data heap and take care of this in a very low amount of code, taking advantage of recursion, another thing we need to emphasize and learn in this course, and be able to clear out and perform good memory management. So in main, in test RBT1, so we don't have anything we're going to code here. I'm going to run make test RBT. Yeah, test RB tree 1, excuse me. all I have in that folder, see, it compiles and doesn't print anything out. But if I do test rbtree1.cpp, all I have there is I use the default constructor, I use the assignment operator, and the copy constructor. So what I've done there, before I did anything else into the tree, is make sure that I meet the rule of 3 requirement. From there, I'm now going to be able to build and implement rotations. So let me show you the last little bit from RBTNode.h. I'm going to show you something that we've added. So this code is provided for you if it ever decides to actually connect. Here, I'll just read it off the slide while it's doing that. So this method is called moving down. And in several instances, when we worked on insertion and deletion, we were able to move elements down into the tree based on our rotation. And so the way we test this, first we check to see if the parent's not null. Then we see if the value is on the left. Then what we're going to do is we're going to say the parent's left element, so parent before, here is pointing to the left, is now going to point to end parent, which is new parent. And then it's going to update it here. End parent's parent becomes that old parent's value. And then parent is equal to end parent. So this allows us to be able to change the rotation and then use all 3 of our pointers. So before we only had 2, and when we get back display trees and probabilistic trees, we're going to be back to having only 2 pointers. But here, this allows us to be able to move the elements down and keep track of all 3 pointers in the red-black tree. Next, we need to determine if the node has a red child. So basically what's going on here is if left's not null and left is red, or if right is not null and right is red. So this allows us to, first, again, we check to make sure that it's there, and then if it's there, we perform analysis of the contents of the node. So now we're going to learn how to code up one of these rotations. So please go to line 57 in the file RBTree2.h. I'll give you a moment. So when you get here, you're going to go past this method that says search. And so while you're bringing that up, I'm going to quickly describe what this search method does. It creates a temporary pointer equal to the root. And it says while temp is not null, if search val, so basically I'm performing a divide and conquer. So if the search val is less than, I set it equal to the left temp node, and we keep going in a while loop until I either find it, which is what happens here, or if it's right, if it's greater than, we just keep going to the right. So that else statement says, oh, it's greater than, I'm going to go to the right. So we have a search method. So in problem 5, we are going to write the left version of this particular method here. So we're going to call it void left rotate, and it's going to take in a red-black tree node that's a pointer and called by reference. So let's do it this way. We're going to do void left rotate, and we're going to bring in RBT node, and that's going to be a pointer, and we're going to want to update the pointers within that node, so we're going to call it by reference. And this one, we can, just for simplicity, we're also going to call this variable x. So let me zoom in a little bit so everybody can see what's going on here. So in order to rotate left, the first thing we're going to do is we're going to create a new node called end parent. So that's going to be for new parent. So RBT node, pointer, end parent is equal to x's right pointer. So we're going to left rotate. So what we're setting up here is we have a value x, and its pointer points over here. And since we're rotating to the left, we're eventually going to want x right to be the new parent. The next thing we need to do is account for the scenario in which we are at the root. So if x is equal to the root, Then what we're going to do is we're going to say the root is equal to n parent. And what this means is, let's say I had 10 and 12, and something down here makes me want to rotate. So let's say 10 is the root. What this allows me to do is it says, all right, before I do everything else down here, I'm going to say the parent I have n parent pointing here, and then I'm going to update root to point to that location. So n parent is pointing at 12. So now we can say that when I'm doing this rotation, I can maintain where the root pointer is pointing to. This allows me to ensure that we maintain the integrity of the data structure itself. The next thing I'm going to do is I'm going to call this move down method that I was just describing to you. So we're going to pass move down, and we're going to pass n parent. The reason why we're doing this is because that previous method helped us keep track of all the movements between those pointers, right? So we have 3 pointers in each of these 2 nodes, and we have to make sure that everything's lined up correctly. We've already accounted for that in move down. So x is going to move down, and then parent, which is now pointing up, is going to be the next parent there. So now the next thing I'm going to do is I'm going to say the old x right is going to be equal to n parents left. And this allows us to connect x with the new parents left element. And so before, x right was n parent. So before, if I had 10 and 12 and I moved it down, 10's right is still technically pointing here. So now I can say whatever was over here, that's what 10 is pointing to. 2 last steps, and then we'll be done with the coding aspect for today's lecture. What I need to do next is I need to say, well, if n parents left, which we just did, if that's not equal to null, then we have another step we need to do. So if n parent left is not null, now we need to set n's left's parent equal to x. So before, this is 10, 12, and let's say this was 11. And so we've updated, we've performed this rotation, but 11's parent is still pointing up here to 12. After we do this rotation, we want 12, 10, and 11. So 11 has to point back here. So that's what we're going to do here. We're going to say n's left parent is going to be equal to x. Right, does that make sense what I just did there? And now the last thing, because we're rotating left, the very last step, we're going to say n parent left is equal to x. So let me scroll up here. I'll scroll up just a little bit. So there's the whole thing. We have n that initially create a pointer. It's going to be the new parent. We set that equal to the right. We're going to say the x is the root. We make sure that we can actually find the data structure. Then we're going to move x down so we can control all of that pointer movement using that move down method. Then we're going to say that the right pointer of x is going to be equal to the new parent's old left pointer. Then we're going to say, well, if the new parent's left pointer wasn't null, well, then we have another issue. We need to make sure that we're pointing back up. I'll get to your question in a second. And then last but certainly not least, we have to update n parents left. Okay, so what's your question? You're going to ask what? I'm sorry? If I could draw it again. All right, so what's going on here is we have, for example, 10 and 12, right? And we have some sort of scenario in which we need to rotate this over. So the first thing we're going to do is we are going to create a pointer, n parent, that's going to point at 12. Then we have to account for the scenario in which 10 is the root. So if 10 is the root, we would need to move the root to point here. If it's not, we just ignore it. Then we're going to move down. So if we do this, what's going to happen is 12 10's parent is going to point to 12, and 12 is going to point over here. So we're actually moving these around. Then we're going to say x right, which is initially here, which is 10. This is going to point to whatever n parents left was. So let's say I had 11 here. 10 is now going to point to 11. That's right pointer is going to be over here like this. And so if it was null, that's fine. If it's not null, we have to make sure that 11 is pointing up back up to 10, which is what this line of code is doing. Then finally, we say n parent, which is 12. We make absolutely certain that it's pointing at 10. All right, did that address your question? All right, any other questions? All right, I don't see anything in the Slack at the moment. Right rotate is the exact same thing. If you look at the code there, it's just going to be the exact same thing in the opposite direction. So I'm going to save that. Let's check to make sure I did everything right. So here's all the code. You can refer to it there as well. And so let's go this. What I want you to do is I want you to run make test RBTNode.h. A pre-order, we did all that. We'd already did level order. Make test RBTree2. And it appears as though I have done it correctly. So while you're doing that, first, if you've done this correctly, you do ls, you will now see problems 1 through problem 5.txt in your folder. The next thing I want to show you is the slide that justifies all of these outputs. So I have created tree 1 through 3. So what I did in test RBTree2, I'll show you here, is I created a tree, and then I inserted elements. Then I printed it, and in that print, we used that. I basically took that exact code that we use for pre-order, in-order, level order, and post-order traversals, and it prints it all out. And then what I did is I used the assignment operator, tree2 is equal to tree1, and then I inserted 2. If you did everything correct with the assignment operator and copy constructors and with the pointers, it'll print out 2, and if you print out tree1, 2 will not be in there. And so I did that, and it worked. And then the last thing is, I set tree3 equal to tree1, and then I inserted 6. Tree2 should not have the element 2 in it. Tree1 should not have 2 or 6. Tree3 should not have the element 2. And then if you review everything that's available in the slide as well, we see that it does in fact print those all out as we expect. All right, does anybody have any questions about red-black tree insertion before we continue on to deletion? Okay, so let's continue on. Just like with red-black trees, they were inspired by the creation of B trees. So it's the same kind of thought experiment. And we're going to do things a little different. Instead of using all the way to the left, it's in the middle. And we're just going to do the same concepts as we did when we did red-black tree, B tree insertion. So here, I'm going to say let's delete 14. So here's what's going to happen. 14, we would just move 11 over. And then since it's in the middle, we would consider that to be a black node. So what you're going to see over here is you're going to see 14 gone, and it's just going to get 11 moved up. The next thing we're going to do is we're going to delete 4. So let me go back here. Here's what's going to happen. Just like with a normal binary search tree, we're going to grab the largest element to the left and move it up. So we're going to see that 2 is going to come up here, right? So now we have an interesting thing. We don't have a good balance. So we see that we have this scenario in the red-black tree, and it matches a similar scenario here. So what I want to do is I'm just going to describe to you the process of how this works. You don't need to memorize it. I just want you to see how it's a little different than the B tree. If this was a B tree, what would happen is I would move 2 down and I'd move 5 up and move these over. The issue is that doesn't give us the balance. So in their thought experiment, what they chose to do is they said, well, 6 will move up and then 2 and 5 will move down. And so what will happen is this performs a rotation. 6 is going to move up and then 2 and 5 will reorder. And so the way this will work is that 2 comes down, 5 moves over, and now 7 is by itself. And so we're going to go over the rule for a red-black tree that makes that happen. The crucial thing that you should see here is that by performing this specific rotation, we now have a path. So to every null element in the red-black tree, it goes through 2 black nodes. So we're maintaining this relaxed balance. So now we're going to delete 8. So what's going to happen is 7 is going to move up since 7 is the largest element. So let's see what happens here. Now we have, for a B tree, we'd have an empty element. So now we're actually going to perform this borrowing again, right? So we're going to see 6 moves down, 5 moves back up. And so what's going to happen is 5 is going to move up and it'll become red. 6 is going to move down, and since it's the only element, it'll be in the middle and it'll become black. And 2 will remain here, and that will become black. How that correlates to the actual red-black tree is that when 5 moves up, it's going to be 7. You're going to see 5 here, 6 will get moved down, and 2 will be here. When 5 is red, and 2 and 6 are black, and 7's black, we now have maintained all of our rules again. And so that's how we get there. Now we're going to delete 10. So what's going to happen is we're going to see 9 is going to move up. And now we see that we have a specific issue here. We don't have the same number of black nodes on each path. And we also see that we have, from the B tree perspective, an empty cell here. So the way that they did this is that they would move 9 down and combine it like that. And now, to get to any null pointer, we have 2 black nodes. Now we delete 11, and when we delete 9, we're going to see that it'll go straight to 11 and then recolor 11, because the 11 will just move over and become the black node here in the middle. So to be sadistic, I likely tried to delete 11. Yes, that's exactly what I did. And we now see that 11's gone. So now we have to somehow meet these new rules while balancing this all out. So here's what's going to happen. We're actually going to be doing a right rotation, because we need to make sure that we have everything that we want. This is going to move down. We're going to see that 5 is going to come up. 5 will be labeled as black. 6 will be here. 7 will be red. And 2 will be here as black. So watch what happens. 7 is going to come down. This cell in the B tree example will go away. 6 will remain here and 7 will be here. Since 7's over here, it will be red. 5 will move over, and we're going to see that this pointer's here and that this pointer's here, because we want that to be in the middle to represent black, and that's what we end up having. Then if I delete, it's going to be deleting 5. So if I delete 5, it's going to move 2 up. Now watch what happens. We move 2 up, and now we don't have the same number of black nodes on each path. So what we're going to do is we're going to see a rotation here. And if we were doing this, it would be the same way. we could have 6, 2, and 7. If we move 2 down and 6 up, what we're going to see is that 6 will be here in the middle, 2 will be here in the middle, and 7 will be here in the middle. So as a result, when we perform that rotation, we're going to have 3 elements and all 3 nodes will be black. Does that make sense? We're going to be walking through several red-black tree examples for deletion. If I delete 2, well, now what I want to do is I'm just going to, I don't have anything to borrow, so 7 is just going to move up and 7 will become here. So 6 will be in the middle as a black node and 7 will be over here as a red node. And then finally, if I delete 6, it'll just move 7 to the middle. So what we're going to work on, I'm going to briefly present 4 different cases that we need to evaluate when performing red-black tree deletion. And then we're going to walk through an example, and then you're going to do an example problem. So for the key for these 4 rules, V is known as the replacement node. So let's say I deleted an element and the largest value on the left came up. That value that came up is now known as the replacement node. For the other ones, I have parent and child, just like before. And then C1 is there for potential child. I have S for sibling. And then I have this other this other blue triangle. This blue triangle, if you see that, the rule is irrelevant whether or not the value is red or black. All right, does that make sense so far? All right, so we have first case 1. I have the replacement node and its sibling is a red node. So that method that I showed you about is sibling red, this is where we're going to start using this. So first, if the sibling is red, then what's going to happen is I'm going to perform a rotation. So I move this up and the sibling's red, so now I'm going to rotate it. So you're going to see just what we coded here, left rotate. We put the sibling's left child to the parent. We put the parent's right child to C1. Then we're going to rotate about the parent. So now it moves up here. So the node locations are the same, but in terms of visualizing it, this is cleaner. And then the last step is to recolor the sibling and the parent. And then I add a note here that this is not a terminal case, that this will always take us back to another case. For case 2, the sibling is black and both of the siblings' children are black. And we don't know or care what this color is for the parent. So what's going to happen is we are going to recolor S to red. Then what we're going to do is if parent is red, this is going to take us to our new case 3. And if the parent is black, we're going to recursively go up the tree. So if we see this scenario here, we're going to eventually counter one of these cases later. So let me walk you through this again, because this is going to be important when you're going to definitely encounter something like this on the final exam, where you'll be expected to perform a big rotation, where at first you're going to need to recolor the sibling. So this rule, the replacement, its sibling is black and both of its children are black. So this means we've moved it up and we've thrown the balance off. So now we recolor red. And then if it's red, we're going to hit case 3. So if it's red, we're going to get this double-double. And if it's black, we're going to recursively go up the tree. So now we're going to go into case 3. Case 3 is that scenario where we have the parent is black. I'm sorry, case 3 is the situation where the parent is red. So we have this double red scenario. So we're going to have to fix a double red here. So here we have the sibling is black, the right child is red, and the left which is that green tree C1 is either color. Bless you. So the first rule is we evaluate all of this and we rotate the sibling about the parent. So what's going to happen is we have the sibling, its left child is going to become the parent, and then the parent's right child is going to become C1. So take a look at that. Everybody see that? So I'm going to try to be slick and plug it in the laptop while simultaneously lecturing. The next thing we're going to do, there we go. The next thing we're going to do is we're going to swap the colors. So the parent, we don't care what it is, but it's the original sibling is now going to be whatever that color was, whereas the old parent is now definitely going to be a black node. And then we recolor the child to C2. The last case is this scenario, and I only really have X in there as a placeholder so you can see the full rotation. The V sibling is black. Its right child, or the sibling is black, but its left child is red. So we see that C1 is red and C2 is black. So what's going to happen here is we're going to perform a rotation and move this up. So what you're going to see is C1 is going to become the right child of the parent, and then the right child of C1 is going to become the sibling. So now what happens is this takes us to case 3, and now we have everything set up. So what I'm going to do next is I'm going to walk through the deletion process for an entire red-black tree without the B tree analogy. And then to conclude the lecture, you're going to work through a sample, and I will work you through the solution. So here's an example of deleting the red-black tree. And so between this one and the sample problem, this will cover every possible scenario that you will encounter on both the left and the right. So first what we're going to do is we're going to delete 25. So when we delete 25, what's going to happen is it's a leaf, so we're just going to delete it. And then what you're going to see is we're going to replace it with a null pointer. This becomes the new V. And then we compare it to its sibling. In this case, 12 is black. So in that scenario, we have null technically counts as black in this scenario. So what's going to happen is 12 is going to become red and 15 is going to become black. Does that make sense to everybody so far? So now what I want to do is I want to delete 15. So watch what happens. I'm going to delete 15, so I'm going to set the parent right child equal to 15's left child, since 15 is not a leaf. So now that it's happened, we're moving this up, and then we're going to recolor that left child. So now we're in that case 1, and then we're going to free 15 from the tree. So when we make it look neater, it now looks like that. So we still have met all of our rules. We still see that we have this relaxed balance, because this relaxed balance, we have more elements over here, but this is 2 and this is 4. So we still meet that 2x requirement, and we prove using our understanding of big O notation that this is still log n. Now we're going to delete 12. So now I'm going to get rid of that. And now we're going to do the same thing. We're going to replace it with null. So now that becomes the replacement node. Nulls in this case count as black. So what we're going to do is we're going to say, all right, now the sibling is red and it has 2 black children. So what I'm going to do is we're going to rotate right to fix the double black. So it's going to be opposite of what we just wrote. We also are going to count that scenario where we're going to say that 4 is going to become the root. So 10's left child becomes 5. 4's right child becomes 10. And then we're going to rotate. And then the last step of this case is to recolor. Now, does anybody see an issue with this particular tree? So we can either point it out to me here or tell me what's up in the Slack. There's something very weird with this tree here. Anybody notice it? Do you have your hand up? Yeah, go ahead. Yep, absolutely right. 5 and 10, this is not a valid tree because we don't have the same number of nodes. And I see that somebody's typing up, but I bet that's going to be the right answer. So now we got to account for, there we go. So 10 and 5, this is not a valid red-black tree. So what we're going to do is we're going to do that last step. We've now moved to the last case. We're going to recolor. 10 and 5 are going to change colors. And so now every path to every null pointer in this red-black tree goes through 2 nodes, 2 black nodes. So very good, good job. So now we're going to delete 3. What's going to happen is we're going to see that 4's left child is now going to point at 2. 2 is going to get recolored. And then we're going to free 3. And now we have this tree. Now what we're going to do is we're going to delete 2. So 2 is going to be gone. We're going to replace 2 with a null pointer because that allows us to correlate it to our rules. And now we see that the sibling is red and its left child, the sibling is black and the left child is red. So in this scenario, this allows us to be able to perform this rotation. And so that was that first step. So remember this case 4. So let me go back. So what happened is we have this case 4. The left child of 10 is going to point to 5's right child. The right child of 4 is going to point to 5. And then 5's right child is going to point to 10. So now we have this scenario here where we're going to have 4, 5, and 10. And then we get to that other case where now we have null, the child is red, the sibling is red, and it has black children, which means we're now going to perform this rotation where 4 is going to become 5's left child. We're going to recolor and rotate. So that was just like what we did in the deletion example. And then last couple of steps here, we're going to delete, went a little too far there. We're going to delete 4. We're going to delete 5, so it brings up the largest value on the left, which is 4. And in this case, it would be just like the initial example. 10 is going to get recolored, like so. If I delete 4, what's going to happen is the root is now going to point at 10. It's going to bring 10 up, and then we go all the way back to our original rule that the root node must always be black at the end. And then I'm going, for interest of time, since it's 53, this is available to you as well. What I'd like you to do, we're going to conclude lecture. I want you to do problem 6. That's available there. Please take 5 minutes, and then we'll go over a solution. So run make problem 6. And that's the specific problem. You have 5, 16, 12, 14, 13, 9, 6, 18, and 20. 12, 9, and 6 are going to be our deletions. In the interest of time, what I'm going to do is I'm going to put the whiteboard up on the screen, and I want you all to walk me through the process. So I want to make sure we can accomplish this and complete this in time. All right, so I've got my red and black markers. What's my very first step? So I'm inserting 5. What's the first thing I do? Simplest step. Who wants to take the easiest one? Yes. Yep, so what's going to happen is, in the very technical sense, we initially insert it as 5, and then it changes to 5 here. I'm just going to leave these caps there. That'll make life easier. What's the next step? We're inserting 16. What happens with 16? Wants to give it a try. Yes. Very good. Now we're going to insert 12. What do I do? What's the very first step? You had your hand up. You want to give this one a try here? I'm sorry, you had your hand up. My apologies. You're going to insert it as red. Very good. So it goes here. So now what's going to happen? What's going to be this result here? What are we going to do here? Yes. Very good. So we're going to do this rotation, right? And now what's going to happen here is we're going to have, this is going to come up. So 12, let me move this a little over here. So we're going to have 12, and then 5 and 16 are going to be, so in this case, we would move it up, and then 12 and 5 get recolored. So it's going to look like this. So what's next? We're inserting 14. What should I do here? What's the first step? Yes. Oh, you're scratching your head. Give it a try. Light blue shirt. So now we're going to say, and so now when I have this rule, where I have 12, 5, 16, and 14, what am I going to do specifically to 5 and 16? Yeah. Oh, no, I didn't have your hand up. Yes, go ahead. Very good. So we're going to recolor 5 and 16 here. Okay, so now we're going to insert 13, right? So 13, in the interest of time, 13 would go here. We perform a rotation. 14 becomes the new subtree root. And this is going to become, 14 is going to be black, 13 will be red, and 16 will be red as well. So now we're going to insert 18 and 20. So 18 would go here. And so now we have red, and these are both red. So what we're going to do is we're going to recolor 13 and 16 to black and 14 to red. Like so. And then we're going to insert 20. So if I insert 20, this now goes here. And now I have this same type of thing. So if in the interest of simplicity, 18 is going to become the new black node. And then we're going to have 16 and 20 over here. So with the insertions, we are going to have all of our black nodes. So in the interest, what I'm going to do is we're going to delete 12, and we see that 12 is going to be moved up here, and 5 is going to move up. And then what we need to do is we need to come up with our specific type of rotation. I'm sorry, I feel like I missed a step. Yeah, I missed several steps. My apologies. So this should be the end here. This should be 6, 5, and 9. So that's the full tree there. And then what's going to happen is 9 is going to move up. And then what's going to happen is that 9 will become black. Then we're going to have 6 here, 5 there, and then the rest of this tree on this right-hand side is going to be the same. In the interest of time, let me draw up the final element. I can redo this, but here we'll do 14 is black, 18 is black, because we're going to delete 9 and then 6. So you can see that 6 is already going to come up. So 14, 18, 5, 13 is going to be red. Then we have 16 and 18. Oh, sorry, this is 20 over here on the right. And I believe that's choice C. I forget exactly which choice that is, but if you put in that last choice and get that solution and run the test script, it should give you 190 points. So I'll make sure I go over that last little bit on Thursday, and then I'm going to go into 3 different C++ standard template libraries that implement red-black trees. And then we're just going to hit the advanced portion, the last little bit. So we're going to hit splay trees, probabilistic trees. We'll hit binomial heaps, and then cuckoo hashes. And that will conclude our semester. Okay. Does anybody have any questions on red-black trees at the moment? All right, on that note, it is 2 o'clock and you are dismissed.